Hi everyone, my name is Lucas,
I'm Michael.
And I'm Kaushal.
and we're going to be talking about supercapacitors. So energy demand is at an all-time high right now. So we're creating a lot of energy and we're using a lot of energy. Was that from you? Okay. So we need a way, and since like for solar panels, most of that energy is generated in the middle of the day, but we actually use most of our energy at the end of the day. So we needed a way to store the energy because we can't use it right away. And there's two ways to store energy. One way is with batteries, and one way is with capacitors. And so a battery stores a lot of energy, but it can't emit the energy very fast. And a capacitor is the opposite. It can't store a lot of energy, but it can output the energy really fast. And a supercapacitor is kind of a mix of the two. It can output a lot of energy pretty fast, and it can store more energy. So this has a lot of uses. Like the group before us talked about, electric cars can use it to accelerate really fast, like Teslas, and so the cars can charge fast, like buses can charge at each stop they make, and like at ports, the big loads that they carry when they're coming down from the cranes, you can also use capacitors to collect that energy and store it as well. Yeah, and so you can make a capacitor, a supercapacitor, by using nanoparticles because they have more surface area, which allows them to store more energy. And we're going to now talk about the experiment we did and the analogy.
So starting with the analogy, so when you make supercapacitors, which are a more recent invention than capacitors, so you kind of start out with a capacitor, which is kind of two plates far apart. One is positive, one is negative, and that's going to create energy for you. Oh, sorry. Should I repeat that? Did anyone hear that? Okay, so you have two plates in a capacitor, one which is positive and one which is negative, and that's how you're going to get your energy. So that's what you start with for a supercapacitor. And then what you do is you put ions in between them, some positive and some negative, and then basically those are going to get attracted to the two plates. And so say you have the positive plate, all the negative ions are going to get attracted to that, as we kind of see, and then you're going to get basically a negative plate next to the positive plate. And you're just going to put kind of a small barrier to prevent them from touching, but they're going to be incredibly close to each other, whereas a capacitor is like maybe a couple micrometers apart. The supercapacitor is going to be like on the length of just atoms apart. So then this is for us. So as you can see in the picture, the supercapacitor is going to have more energy as represented by the love meter. So which is kind of just total energy, whereas a capacitor kind of on the left, since it's not going to be able to store very much energy, so that's kind of represented by the love meter, and then as you get closer together, that's able to store more energy. And then also, so capacitors, you can also think of it in the sense that the people on the right are probably in more of a long-term relationship, which is why this is able to store energy over the long term versus people who are just kind of casual, So that could be another way to look at it. So then getting back to our experiment, we actually were able to make our own supercapacitor. And we used activated carbon in our supercapacitor. So the two plates are going to be made out of electrodes, and this is the carbon, and this carbon is on the nanometer scale. So it has an incredibly high surface area to volume ratio, because things that are really small, they have a lot more on the outside and not as much on the inside. So you're going to get much higher surface area. For a small capacitor, you could still have like a football field size in terms of surface area, because of how small all the particles are. And so when you have this high surface area, that's going to be able to create when they're super close, you get that much larger electric field, and the much larger surface area is going to create much more energy. So now there are limits to this analogy, obviously. So to explain that.
Okay, so one thing that this analogy doesn't address is the difference between power density and energy density. So as you can see, a supercapacitor, they get very close, so they're capable of storing a lot of energy, and they can do it rather quickly. This is a little different from a battery. A battery is able to store a lot more energy than a supercapacitor or a capacitor could, but the problem with a battery is that it can only discharge that energy very slowly. And so that's why you have batteries that charge in about 3 to 5 hours and take about 3 to 5 hours to discharge. Supercapacitors can deliver a lot of energy very fast, and they can store more energy than a conventional capacitor could. So in terms of energy density, a battery is the highest, followed by a supercapacitor, followed by a capacitor. And then in terms of power density, it's a capacitor is the highest, and then you have a supercapacitor, and then you have a battery. And as Michael mentioned, as you increase the area, there's just more space, especially through nanoporous materials. There's just more space for electrons and charges to gather, so that increases the strength of your electric field, which increases the strength, which increases the amount of energy that you can store. So as Luke was mentioning at the start of the presentation, one of the applications for this is cranes. So if you go to the docks, they have cranes that unload shipping containers from large vessels, and those cranes need to use a lot of energy really quickly because they have to basically lift very heavy containers up and down in very fast. And so currently one of the big problems is it takes a lot of diesel fuel to actually accelerate the crane up and bring it to such a high position, but then when you actually are bringing the load down, you obviously can't really, you can't recycle that energy with the technology that's currently available. So that's why if you use a supercapacitor on a crane, you could be able to charge that supercapacitor while you bring the crane down, and then you can use that stored energy for the next lift. Lucas also mentioned applications in electric cars. I think the previous group also mentioned this. If you have a Tesla, they have supercapacitors which enable that instant acceleration, because those supercapacitors can dump large amounts of energy into the electric motor very fast. And then buses, that's also another example that was given. So a bus doesn't need to store that much energy for that long a period of time. So as it goes from stop to stop, it can recharge itself. And then finally, for energy demand, supercapacitors can enable us to store larger amounts of energy and be able to, discharge that a little bit faster when you have, say, solar panels that are generating electricity at 12 p.m. when you want to use it at 5 p.m. once you get home from the house, to the house. And so with that, thank you. And any questions?
So you guys, and I think also the previous group mentioned cars as a potential market for these technologies. So if you think about the Ragone plot, right, the power density versus energy density, and you kind of outlined where batteries, capacitors, and supercapacitors lie on that, where's a combustion engine in comparison to those technologies, and how close or not close are supercapacitors to reaching what a combustion engine can actually do right now?
So on the Ragone plot, an internal combustion engine is actually at the top right-hand side, which means it has very high energy density and very high power density. And supercapacitors are a little bit more towards the middle and probably the lower end vertically. So they're not quite close, that close to combustion engines, but they definitely are closer than capacitors or batteries taken alone.
You can't beat chemical fuel, unfortunately, but we have to. So
Assuming comparable energy and power density, of these three technologies, how do they compare in terms of size and weight and cost?
So, from what I understand, batteries may be the most expensive to manufacture because they require the most complex materials because there's actually a chemical reaction that's taking place inside. Also, as was mentioned in the earlier presentation, if you have a battery, you need to be able to ventilate it properly so that temperature changes don't affect it, and you don't need that if you have a supercapacitor or a capacitor. As opposed to pricing, from what I understand, you need more material to build a supercapacitor, so it would be more expensive than a capacitor.
Yeah, so I think about this a little different. So the question is, for a given amount of energy stored, which one do you think would be the lowest cost?
Capacitors would be the most expensive, and batteries would be the least expensive for a given amount of energy stored.
Yeah, that's the issue.
Batteries store so much more energy.
Batteries store way more.
Yeah.
So it may be cheap to make a supercapacitor, a capacitor, but they don't store much. And the materials are actually, they all have to be cheap because everybody wants cheap storage. So if you have an idea for an expensive battery, you can have your idea all by yourself because nobody is interested. Okay, another question? One more parent question? Okay, so I have a question. So you described this picture as a continuum from a capacitor to a supercapacitor. But can I ask you to look at this picture and consider also describing it as a continuum from a capacitor to a battery, and then comment on how it might map onto that continuum?
So I mean, if love was energy, then the rightmost relationship would be a battery because it has the most love in it. And then the leftmost would be a capacitor because it stores the least amount of love.
Yeah, so I think kind of we assumed that the rightmost one was a supercapacitor since they're so close together, which is kind of what makes a supercapacitor, two plates. Which
No,
are like,
okay, but what you said was good. So just keep going with this for a minute. So you can map distance with what you said. There is a way that you can also map distance to capacitor, supercapacitor, battery. And what would it be the distance between?
The electrodes on a given.
I guess in a lithium-ion battery, you've still got lithium atoms traveling in between two sides. So would those be even closer than in a supercapacitor?
They would be even closer. They would basically be atomically touching. You'd end up with the positive and the negative thing atomically right beside each other. Whereas in a supercapacitor, one's in the solution and the other's on the surface. So they're pretty close, but they're not an atom distance away. There may be, so you're like maybe 1 angstrom, 2 angstroms away in a battery, and probably more like 1 to 10 nanometers away in a supercapacitor. So I don't know what the artist described, but that may be a different way to map it. But it's all the same concepts that you already showed. It's just pushing it's the same ideas, it's just pushing the continuum a little farther. Okay, all right, so we should thank these guys and ask the artist to stand up.